Hey everyone, and thank you for joining the talk, in which I will tell you a bit more about our recent publication. So let's get into it. So our use case scenario are consumer-grade robots that have to adapt to a user-specific environment. While we've simplified this a bit to just learning specific objects within the user's environment, so that the robot is capable to do its actual task. For the lawnmower robot left, this could be, for example, to mow over all the leaves, but not over the delicious apples. For the right setting, the robot could, for example, learn which objects to clean up, so that the owner has a tidied up room every day, ready to have some company. Our learning paradigm for training the robot is pool-based active learning, where there's an unlabeled and a labeled pool. As the robot drives around autonomously all day, it collects a lot of unlabeled samples placed into the unlabeled pool, as the name suggests. Some of those samples are then queried by the querying function to be shown to the oracle, which is in most cases the user for labeling. Then the labeled sample is placed into the labeled pool and the classifier is trained incrementally with the new sample. Then this process repeats and the next sample is queried. Now, this querying can happen either randomly or, for example, uncertainty-based, by querying the most uncertain sample for the classifier for better classifier improvement. Then, as before, the sample gets labeled and put into the labeled pool and the classifier is trained again. Now, our research question is if the classifier is good enough so we can stop training, because saving human resources is a very big deal for us. But at the same time, we want to accomplish the task to a certain quality. So our goal is to have a module that estimates the accuracy of an incremental classifier with high precision. Further, we want to answer the second question. Does the estimated classifier accuracy relate to the actual task? Speaking about tasks, in our setting we are implementing an inventory robot that has to count object instances within a room. We define a task performance measure, how well the robot does this counting. So here is an example. In the room are placed 5 lemonade bottles, 3 black cups and 4 orange juice bottles. The robot, however, counts 5 lemonade bottles but only 2 cups and way too many orange juice bottles, because maybe the classifier had difficulties distinguish some classes here. However, we calculate the actual task error, which is just the inverse task performance, by adding the number of false negatives and false positives divided by the ground truth number of instances. So in our example, the task error would be 0.25, so we have a performance of 0.75 at this state of training. So to make this clear, we are dealing with two different measures here. First, we have the classifier's accuracy, which we try to estimate to further make assumptions about the actual task performance. Our approach now for estimating the accuracy of a classifier in our setting is kind of a semi-supervised approach that uses confidences of all the unlabeled samples from the unlabeled pool to estimate the classifier's accuracy. I will get into details about our approach in the second part of this video, so if you are interested, please tune in. To test our model in the inventory robot setting, we use the robot to collect a whole data set, not only images but also other data coming from the robot, like the spatial object position within the room. I will talk about this in depth in the second part of this video. But let us first take a look at some of our main results. So here we can see two training runs. The one on the left uses random sampling as a query function and the one on the right uncertainty sampling. The number of trained samples are displayed on the x-axis, and on the y-axis is the absolute accuracy and also the task error And as you can see here, our method in orange can estimate the ground truth classifier accuracy in blue with high precision, while the baselines are farther away. And this becomes even more noticeable using uncertainty sampling, the plot on the right, because the baseline models rely only on samples from the label pool, and those samples are hard to classify because they are very, very uncertain to the classifier. So their estimated accuracy is overall pessimistic. What we also can see from our main results is that the estimated accuracy by our model relates to the actual task error. So for example, we can define a maximum task error of like 5%, and then we can use our model to estimate whether we are below this maximum task error. This was the first part of the presentation. Thank you all for your attention, and now I hope for fruitful discussion. Thank you. Otherwise, I will now continue with the second part of this video. For the second part, let us first take a more detailed look at our new model for accuracy estimation of incremental classifiers. Commonly used approaches for accuracy estimation of incrementally trained classifiers are to do a cross-validation of the label pool, or second, to do an interleave test train error. However, both approaches have the drawback that they do not consider the many samples within the unlabeled pool. So we thought about a semi-supervised model for accuracy estimation of incremental classifiers, which is basically a mapping from confidences of unlabeled samples to ground truth accuracy. And I depicted here as an example for an KNN classifier. So we have a lot of untrained samples here, and now we start to train the KNN model incrementally. And after each trained samples, we can extract confidence measurements of the classifier of all untrained samples, and then we can put them into an histogram of these confidences, which you can see on the right. And together with this histogram, we are extracting also the ground truth accuracy that the classifier has at this stage of training for all the untrained samples. And as the training continues, as you can see here, the confidences of all untrained samples become higher and higher, and also the accuracy rises. So there is a clear relation. And at this stage, we would say that the classifier is probably good enough. So after collecting a bunch of these histogram accuracy pairs, we can then train an arbitrary regression model with the histograms as features and the accuracy value as a target variable to further apply this regression model to other classifiers trained on other but similar data for estimating the accuracy of those classifiers accurately. Now, as I said, we implemented our accuracy estimation model in this inventory robot application, where the robot has to count the different object instances of a particular object class. A possible simplified state machine of such a real-world application could be like this. So first, we start the robot with an untrained classifier. Then it drives around and explores the new environment and captures a lot of object images. And after a while, it asks the user for some labels of these images. And after each provided label, we are estimating the classifier accuracy with our model. And we check whether it is above a certain threshold. If not, the training just continues and the users ask again for some labels. If the classifier's accuracy, however, is above the threshold, the robot can do its actual task. In this case, the inventory, and count, for example, all green bottles in the room and notify the owner to bring them back to the supermarket. After a while, the robot can explore the room again for changes and check with our model if his classifier is up to date. If not, he again needs a human for supervision. So to motivate this topic again, we ask ourselves, if we can apply our CGEM model in this setting on new classes not used for training the model. And again, if the estimated classifier accuracy correlates with the task performance, so that we can use the first to make assumptions of the robot's work quality, so to say. To simulate the robot application I talked about earlier, we used a robot to record an object dataset. Therefore, we drive the robot to fixed waypoints where the robot turns 30 degrees to each side to capture more objects. The dataset contains 10 object classes and an additional clutter class, which we will also use later in our evaluation, where blurry or falsely segmented images are consolidated. However, we not only captured object images, where we used YOLO object detector for segmentation, we also recorded other information coming from the robot and included them in the dataset. Also, we used VGG19 deep convolutional net to extract highly abstract visual features from the objects, also included into the dataset, which we will also use for training the classifiers. One thing we also use for implementing the counting of object instances is the spatial position of a particular object sample in the environment. You can see this in the right plot. I will get into details how exactly we calculated the task performance with this in a minute. Also notice that we published the multimodal robot dataset on an open source data repository, so please feel free to check it out. Let us now take a more in-depth look into the experimental setup. We apply a train-test split on the 10 classes from the recorded dataset in a way that the train set consists of 5 classes and the test set contains the other 5 classes. Then, with the train set, we train the CGEM model as described before by training classifiers on that data and train a regression model from the statistics of the classifier confidences for the untrained data, and the ground truth accuracy we can calculate because we annotated the dataset also with label information. We applied the regression model then on the test classes. We start training a KNN classifier by querying, as demonstrated before, sample by sample. We train a particular sample simulating human labeling by using ground truth label information. And after training, we apply the CGEM regression model to estimate the classifier's accuracy for all the untrained samples in the test set. Then we are evaluating the task performance by considering the spatial x-y-z coordinates of each test sample. By applying a constrained density-based clustering approach, we first create spatial clusters of samples of possible object instances. And further, we used the train classifier to classify all samples of a cluster. Then, by using a majority vote, we define the class of a cluster. By repeating this for all found clusters, we can estimate the number of instances of a particular cluster, and further, by considering ground truth information, because we know how many, for example, green bottles are located in the room, we can calculate the inventory task performance. So these are the results you saw earlier, and they show a classifier's training with exactly this setup, and you can compare classifier accuracy and task error. But I don't want to repeat myself. Also, we included the cluttered sample from the dataset into the train and/or test set. We had 4 conditions here: clutter in both test and train set, no clutter at all, and clutter only in test and clutter only in train set. However, the inclusion of clutter samples was not significant. This is maybe because there were 2 less clutter samples within the recorded data. So to conclude, we implemented a household inventory robot application in which we applied our semi-supervised accuracy estimation model to be able to make predictions about the robot's performance in this task. We confirm findings from an earlier contribution But further, we trained the model with different classes in the train test split. Finally, we found out that our model could be used in such a robot setting, improving human-robot cooperation by saving human resources. By having a self-assessment built into the robot, we also hope that this will increase the acceptance of the robot as a cooperation partner. Finally, this is the real ending. Thank you for listening. If you have any questions or want to discuss something, please hit me up.